that's you'd rather not.
Yeah, no, I think that's fine
Okay.
because we're going to have, there are going to be a lot of questions and we're going to have the discussion.
Okay,
now and then.
great. The famous Paul England has entered the room over there. Okay, so I've switched the presentation. I'm going to describe the Nexus boot because that brings up a bunch of policy issues I'm going to talk about privacy, who controls the machine, where the keys are, who controls the keys, the whole panoply of policy questions. So, first of all, booting a Nexus is a misnomer. It could happen if you did a virtual machine monitor, it really would be a boot. You'd start up the virtual machine monitor and the Nexus when you booted the machine. But as constructed now, and another reason we didn't do the virtual machine monitor is you can start the Nexus anytime. You actually initialize the Nexus, don't boot it. So I'm going to do an abstractly accurate, but not in detail accurate description of how a Nexus boots and what happens. So you're sitting here running happily in your left-hand side applications, and you decide to boot a Nexus. And the machine has roughly been set up so that however the Nexus initialization happens, there's administrator privileges to start up the Nexus associated with it, whatever the panoply of things that starts it up. That means not necessarily the person who says, I need a trusted application is an administrator, but somehow the booting a Nexus is something associated with administrator privileges. On the left-hand side? Okay, so left-hand side says, okay, boot up that Nexus, and it points to a file, which is the Nexus. And again, the left-hand side is unprotected. It can point to any file in the world. So it just says, here's the file to boot the Nexus. The left-hand side operating system sets aside the memory, the physical memory that file is going to get loaded into, and loads the file in. And then the following things happen atomically. They don't happen independently, so you can't sort of interrupt the thing in the middle, which goes to a question, during initialization, what can go wrong? So the following thing happens initially. The first thing that happens is that physical memory, using some mechanism, which Mark described, is removed from view from everybody else on the machine, including the operating system. So if the operating system tries to use that physical memory, read it or write it, it gets a hardware exception. Okay. That area is fed to this TCAAB, the chip, the smart card core, to get hashed, get a cryptographic hash. And the cryptographic hash is stored inside that chip. And actually, that chip also knows, roughly, this is abstractly, that the Nexus is in these physical address locations. Okay? The processor priority set high. Control is transferred to the beginning of the Nexus. The Nexus gets to do whatever it wants to initialize itself. So, for example, it will set up some interrupt tables. So if it's interrupted during Nexus operations, control gets sent to the Nexus, not to the left-hand side where it could do bad things. And then it just returns to the left-hand side. And the left-hand side can start up a program the way it would start up a program anytime. Now, the whole idea for storing the hash of the Nexus in that chip is the Nexus can now make two kinds of requests to that TPM, two kinds of hardware requests. One is unseal something. Here's a blob. Unseal it for me. You know my program identity, so you know to unseal. You have stored secrets for me, which you can use to unseal blobs I hand you, encrypted blobs. And the second function the hardware can do is say, here's a blob, please sign an attestation statement for me, which means basically take the blob, append the cryptographic hash which you've stored of me to the message, and sign it. That's when I get to do the attestation. Those are the two hardware things that the boot process allows to happen. And just to be clear, those two operations happen very early in the use of the Nexus. And that TPM chip, that smart card core, probably doesn't get used at all after that. So what happens is the Nexus will make up its own secrets and store them cryptographically. It will say, unseal them for me. And after that, it doesn't need the unseal operation anymore from the hardware because it's got the hardware, it's got the secrets stored in its little protected memory. And it probably has public keys that it's negotiated with other people using the attestation statement before. So it probably doesn't use, in the typical invocation, the attestation, hardware attestation at all. It only uses that to acquire new key or to get agreement on new keys. So that's the boot. Oh, shoot. There's one important thing I didn't tell you about. There's one other operation that happens atomically. I said the image that's going to get initialized gets handed to the TPM chip, the smart card core. Once it's hashed, the hash is compared to a list of hardware hashes of the Nexi users, people in physical control of the machine, said are allowed to boot. So you can't boot a Nexus unless the user said you can boot it. Okay? So
at the initial configuration, you say these are the Nexi that I trust.
Yeah. So and this brings up another question. So the way to think of it for this purposes of this talk is the first Nexus you authorize to boot, you're roughly going to type in the cryptographic hash through a hardware virtual path, and that's it. And probably that Nexus will have permissions to add other Nexuses to the list, so you don't have this horrible user interface problem. And probably in a corporation, the IT department is the guy that types in that first, Nexus hash.
Is there evolution, upgrade?
Yes,
Nexus?
we'll talk about upgrades. So, and the crucial thing of upgrades is how do you upgrade keys? And I can never get to first base before I get. So here's how it actually works. When I seal a secret, what I do is I don't just say seal it. What I say is, here's the secret hardware, seal it. And here's a cryptographic hash of a guy who can unseal it. Here's a cryptographic hash of a Nexus that could unseal. We're just talking about Nexus. There's a more flexible version for applications, which I'll talk about in a minute. And so what happens is when you want to upgrade a Nexus, Microsoft, embeds a public key in its Nexus. And it signs a certificate that says, here's the hash of the new Nexus. Please unseal your secrets for this new Nexus if you want to upgrade. Okay, so that's the boot. The reason I explained the boot is it doesn't depend on the BIOS. It doesn't depend on anybody else in the system doing the right thing. If the Nexus will boot only if the user said it can boot, and that's only mediated by hardware, or it's mediated by hardware, so there's not a software attack on that. The thing that you can boot anything that you say you can boot, but they all have their own secrets. You can't make Nexus A unseal something for Nexus B unless Nexus B said it was okay, period, by hardware. Yes?
Can you comment on the size of Nexus?
This was the thing I said was about 50,000 lines of code, C code, and that's not a really great measure of how big things are. I don't know. It's just a guess right now because I'm not sure. I'd guess a couple hundred K.
And like you would expect to have a machine to have multiple Nexuses?
You can initialize a Nexus at any time, but you can only have one running at a time. You can't virtualize a Nexus.
But typically, it'd be a Windows Nexus and a Linux Nexus, maybe.
I won't write the Linux Nexus. Actually, in print, there's no actual technical reason why you can't run a Windows Nexus under Linux and have Linux talk to it. To tell you the truth.
I mean, in practice.
Yeah, but anybody can write a Nexus. The other policy questions is, we talked about load, and I sort of hemmed and hawed a little bit. So the mandatory, in order to trust the trusted computing base, you have to be able to see it. Otherwise, how the hell do you know it? It's all based on its cryptographic hash. So the Nexus and the runtime and any mandatory code will be available for review, for source code review, generally. And ultimately, that's the trust mechanism. And you should be able to look at it, compile it, confirm that the hash is what, the hash is we said. That's it. You don't have to publish your applications, though. So you can write a big, thick application and say, first of all, you use it internally. You don't care who trusts it. You trust that that's the end of it. And if you do it externally, it's up to your whatever the contractual agreement. If you tell people you're going to look at it, they can look at it so they can believe it. That's fine. If you want to give it to a third party to sign something that says it's believable, that's fine. But the mandatory trusted computing base will be available for review, period, which is involves a certain amount of cultural shift for Microsoft. Okay, that was my booting in Nexus. Threat model, and I'll take the advice of trying to be more careful about what we mean by software attacks in the future. The threat model is we don't want software attacks, and we don't want break once, break everywhere hardware attacks. Let me explain what that means. We expect a determined, intelligent adversary could break the hardware. But we don't want the break of one piece of hardware to affect another piece of hardware. So that's our hardware model. Again, for the commercially available, everybody gets it. It costs $5 extra version. I don't know what it'll cost to break, $100, $200. The FBI, with their 2,000 wiretaps a year, will have no trouble being able to get it, stuff like that. Now, there is no reason that NSA could use the same architecture and just have much more hardened hardware. There's no reason to stop that, and that goes to your question. You could take the exact same software architecture and just make better hardware for it. But we would like you not have to rewrite all the software again. We'd like you just to be able to use it, including our Nexus. Okay. Hardware keys. So as a result, there are really two keys. I'm sorry, abstractly there are two keys. This is not how it actually is at the moment. But you can think of the TPM as holding two keys. The first key is a signing key that signs attestation statements. And the second key is the thing that seals secrets. The second key can be a symmetric key, actually, an AES key. And the second key gets generated randomly, can get generated randomly. In the current implementations, it doesn't work this way, but I want to talk conceptually for a minute. When you take ownership of the machine. So, and the reason I'm going through this rigmarole is the policy question is who owns the machines. The machine hardware key is owned by the hardware, period. It's not controlled by a person, entity, user. Brings up the question of how it got initialized, but it's not controlled by a person. And the sealing keys are also owned by the hardware, and they're not only not controlled by anybody, they're not owned by anyone. Period. The user gets to say in his sole discretion who gets to use those keys and for what purposes. Period. And again, typically, those are not the keys that ultimately get used. Those are keys that are used to negotiate new keys, which are owned by whatever the application is that's using the keys. And that application may disclose them to the user or not. It depends on what the trust model for the application is. Yes?
The keys are stored in some kind of
in this smart card-like thing?
This smart card-like thing, and there's no way to learn the keys by doing operations.
Yes.
I've seen within the Nexus, I mean, if I just get the machine
Yes.
off like this, man.
That's right.
When you're using the term own, I think you're not using it in the legal.
Yeah, nobody has control over those keys except the hardware. They are not a priority. They're not known to anybody, and they don't have policy associated with them except I'm not going to disclose myself to anyone. Period. Okay, I won't use it. So what term should I use?
A little laden.
Okay.
I think you're saying nobody has access to them.
Yeah.
They're embedded.
Right.
They're not
You use
visible to
control and
anybody.
possess.
Huh?
Control or possess.
Something other than
Control of possess. All right.
If I sell you my machine, and I've gone off and established using that set of keys,
Yep.
credentials at AOL, what happens then?
So let's see how you'd actually use the AOL credentials. You'd use the attestation thing to convince AOL you were a trusted machine. Then you would make up a new private key for your AOL negotiation. And you'd store that using the AES key. When you sold the machine, you would flush the secret, that key. You could still use the private key for attestation, but actually, interesting, the Nexus actually will negotiate its own attestation keys too. Actually, at the risk of, the only purpose of the attestation key is to attest. So one sort of solution that would be nice a priori, if anybody could stick the key in or cause the key to generate, and the public key associated with the entity that did that was bound to it in some way. And that would sort of get rid of all the arguments about who controls, possesses, owns, operates that key. But the hardware expense is too high. And again, or it seems to be too high. Again, the only purpose of that key is say, here, this came from a trusted platform. Okay. So, I'm going to run through these fast, and then I'm going to let Marcus go, because now that you know that, I told you about the two keys. Opt-in. The keys are, the ability to boot a Nexus is controlled by the hardware. The ability for the Nexus to do attestation is controlled by hardware. So it's separately acted. Even if I boot a Nexus, it doesn't mean it automatically has the right to do an attest from the hardware. So it's separately ACLed. It's an opt-in system, or at least we're pushing it as an opt-in system, which means by default it's turned off. The user has to do something to make the hardware work, or to the hardware do this thing. And also, the ability to use all the secrets for each nexus is separately ACLed. So the user is in complete control at the hardware level, and if you use a Microsoft nexus, that same level of control will be propagated to applications. You get to say what applications do in attestation. You get to say which applications get to store secrets. It's separate. Even if they get to isolate themselves, they aren't necessarily guaranteed the right to have access to cryptographic services from the nexus.
Just before you leave that,
Yes.
one of the interesting dialogue points that might get raised is that you're right, opt-in means I have the choice to turn on certain features.
Yep.
However, taking a real critical view, that might be sort of said, look, that's totally opposite to your trustworthy computing mantra, which says that things are going to be privacy by default.
No, it is privacy by default. This is privacy by default because you can't disclose anything from the hardware unless you opt in.
I think what I meant was that some critical views might be saying, well, that you said that things will be shipped with all of the privacy enabling features turned on. There would be no action. And I'm interested in your thoughts on that.
Well, boy, I'm not sure I'm interested in my thoughts on that. What I'd say is, this is the do no harm philosophy. So it is true, and it's an important application of Palladium to be privacy enhancing, to protect your privacy. However, if we give people the right, if it's turned on by default, and actually there's some people in the company some important people in the company who thinks it should be turned on by default for that reason. And what we say is, you know what? We'd like to do no harm. So we want to, if the user, if there's any danger Palladium brings, and the only danger is disclosure of this public machine key, which we want to make sure the user has taken an affirmative action to enable that. So we've always been sort of respectful of the user's rights and making sure they have control of the thing. It's true, if I buy the machine, I'm going to turn it on right away, and if I were running a company, I'd make them turn it on right away. But there's enough suspicion and enough worry as a practical matter that there's bad stuff will happen. And just as sort of a nice philosophical matter, it's like, you know what? We're not going to do any harm. You have to understand enough to turn that thing on, and then you'll understand the consequences.
Hey, John.
I prefer that. Yes?
A follow-up question on that. If it was off by default rather than on by default, then what security features, what security benefits are now?
If we're on by default?
If you're off, in order to do no harm, what security benefits
probably the only thing you really have to do is
missing?
make sure the attestation key you didn't have access to the public key certificate from the manufacturer, because that would disclose the public key, or the attestation function.
So
if those were turned off by default, it's hard to imagine you can do any harm.
That's not my question. I'm trying to determine what security benefit is lost or gained based on how you decide this question.
Well,
if you shift it on, then customers would benefit how immediately?
If you shift it on, if you shift it on, and there were support in the left-hand side for doing machine monitoring, you would not automatically get that. So you can imagine a day when there's think of it as a giant virus, something much more general than virus protection, a thing that made sure the left-hand side was healthy. If it was on by default, that would always be running when you booted your operating system, and you would be safer as a result. Also, if you had applications which were Palladium enabled, they may by default say, do the safe thing. Never disclose to Amazon my private information. Always go through the Nexus and do the blah, blah, blah. So you'd lose those.
So what I'm still trying to understand, though, is if it's off by the, even if it was on by default, I mean, to run a Palladium-enabled app, don't I still need to be asked something by the app as part of?
Well, no, it's up to the app. If the app can run and it gets access to attestation and the certificates, it can give them out.
So,
I thought you had to decide which apps.
No, that's the opt-in. Yeah, sorry, there are two levels. Hardware and the software. At both levels, both of what I said is true. You actually have to expressly turn them on and expressly say what can use them. And so the protection mechanism is I will not let an app that will do those bad things have access to the attestation.
So the answer to Ira's question is that you would still be required to turn something on. It's just whether you have to opt into two things.
Yeah. So okay. So the danger. So again, it's a two-level thing. The danger in turning the hardware on by default is you have to make a choice about what Nexus will run, which means now the user no longer has the trust point for what Nexus can run on his machine, which introduces the first set of dangers, because the Nexus at the next level is enforcing policy about what applications can use all those functions.
So the user doesn't decide what Nexus
Yes,
you
it
decide.
does. No,
Right.
the user decides. And so if it didn't, if it was turned on default, that means whoever manufactured it or somebody early in the chain said, let's enable this Nexus by default.
So John, let's just think about a happy medium then. Is it, am I forced, I use that word kind of pejoratively, but am I forced to make a decision when I first buy a machine with these features on there? In other words,
You can change your mind anytime.
what I'm getting at, though, is that there's a difference between having all these wonderful features in the background that I can choose to turn on versus allowing me or facilitating or even kind of promoting me to have to make certain choices the first time I buy a machine with this or software with this features on.
So this is probably too detailed a question for you. It's probably too early in the cycle. So you're asking, when I install the machine, will I be strongly encouraged to opt in?
Correct.
Or will that
make
have
some choices?
Yeah. Well, you'll definitely have to make some choices when you install it. And it's actually even more complicated than that. If you buy a corporate machine,
Right.
when Microsoft, I don't know, pick a company, when Boeing buys machines from Dell, they'll say turn this on by default.
Right.
But that's okay. That's and here's the nexus. If you're buying an individual machine, it may be that opt-in means when I buy my Dells online. When you buy it online, you say, hey, Dell, I'm going to check off boot up the standard Microsoft Nexus if you're buying Windows, or check off doing the Linux Nexus if you're booting Linux. So it's a little bit of a fuzzy thing, but conceptually, which is all I'm prepared to talk about now, the user at any time has to can enable or disable it, and there has to be some user action. And user, I mean owner of the machine, not the person necessarily who's using the machine that minute. There has to be some owner action that agrees to having a thing run on his behalf.
Are you at the point, though, where that is going to be a physical choice that the user must make at first use?
Again, it depends what he told his OEM to do. But if you got a Virgin machine with no software installed on, yes, it's a physical choice you're going to have to make.
Thinking about an OEM enterprise.
So if you got a raw machine, no software on it, and you loaded up Windows, let's say, you would have to make a choice when you loaded up Windows to turn it on. Opt-in choice.
Great.
John,
Yes.
I seem to miss, how does the user or owner identify that he's owner to the hardware?
Physical presence implies ownership, usually.
So if I lose my machine,
That's right.
whoever picks it up is the owner.
That's right. So if you wanted to protect, the lost laptop problem, you would have a trusted application, and you either put a smart card in, which enabled the application to get access. You double encrypt secrets to some other thing, or do password to protect that sort of stuff. Yeah, but in principle, the access to the secrets are based on the software identity, not the person typing the machine identity, unless something else happens, like a smart card or password.
Will you explain at some point what does it mean that one key is used by seal storage and is randomized?
Yeah. This is a very simple point. So when you seal secrets, as I've described it, if you seal the same secret twice in a row, you'd get the same encrypted blob. So in principle, that would allow an adversary not know what the content was, but know it was the same thing you did before. So when we encrypt things with seal storage, you just throw a little random.
Does it mean anything else?
No. So basically trying to protect against standard attacks.
So it could not mean, for example, that if I look at the ciphertext, I cannot determine whether or not they are encrypting the same key.
Well, what I said implies, by doing that thing, you can tell that.
The identity of the key may well be revealed, right? That's okay. The fact that two ciphertexts are under this key might be revealed by a key identifier. It's just that the underlying clear text identity will not be revealed.
So that's are two different things.
Yeah.
Yeah, but this is some of the ambiguities that we get here.
This is just probabilistic encryption.
Okay.
I should say that.
Also,
I'm actually going to try to race through the slides, the rest of my slides, to give Marcus a chance in about 5 minutes, but go ahead.
So now let's assume a marketing scenario, and you're thinking about consumers.
Yep.
And you're giving them a value proposition.
Yep.
As an OEM, and you're saying, we think you should buy this machine enabled, NGSCB enabled, because there's a bunch of interesting stuff that just happen when you buy this.
Right.
And all of these new security features
Will be enabled.
they'll be enabled,
Yep.
and they're there.
Yep.
Already there.
Yep.
The health on the left side, virus.
Cryptographic keys protected, a bunch of stuff.
Now, in that scenario, would it suffice for the OEM to say, and by the way, if you buy it, since if you buy it, you want it, then we're going to sell it to you with the hardware default on, not off. Now, what privacy harms might occur such that it should still be off, or is that only a perception?
No, that would be okay. Again, if I guess what I'd say, I'm going to garble this because I'm not going to play a lawyer on TV. I think in our minds, it's okay if it's on, so long as the user knows it's on.
But what would you tell the user about
if you were
potential privacy implications by having it on, even though it's for this security reason? That's the value proposition.
What we would say, what the user needs to realize is that a miswritten application that was enabled might disclose platform identity. That's actually the worst. That's the bad thing that can happen.
Is that something that's worse than what can happen on the other side?
Well, no, actually, to tell you the truth, there are lots of attacks on getting your platform identity.
But isn't it the case that could happen? I mean, that can just happen, period.
Yeah, I guess what I'd say, okay, you know what? I'm going to talk to you guys offline. What I'd say is it's not, in other cases, it's not our fault.
That's my point. I mean,
Yeah.
it's not a function of the choice you make whether that scenario can happen. Once you turn this thing on, for any reason.
Let me talk to you separately.
There's a bad
I understand. I totally understand your point.
But can I ask one question?
Yeah.
What if you said, that the Nexus determines, or they determine by default, what other
What
applications could run?
Yeah.
And to the extent that the OEM says, these are the cool things that you're going to get, but doesn't tell them all the other things that possibly that Nexus is going to authorize, that's where you have a problem, I think.
Okay. I'm going to race through these. The other keys are owned by the programs and the people who install the keys, period. We don't have access to any of the keys. You're in complete control. Nexus can't run without permission. No application can run without permission. Key services can't be used without permission. Okay, now the policy. The reason I do this is there's standard complaints on the net which are totally misinformed. And just so you know the right answers, when somebody asks you in class, you can say, everything that runs today on an NGSCB system. Hardware run any Nexus. You can't. There's nothing in the hardware that says you can only run a Microsoft Nexus. And in fact, Microsoft doesn't want to have to sign anything to let you run a Nexus. I mean, in the sense of cryptographically signing. Our Nexus will run any application that the user says it can run. So you won't have to get a signed certificate from Microsoft to run an application. You might want a signed certificate from Microsoft to say, we looked at this application, or we wrote it, and we think it's OK. But you can run whatever you want. You know what? This is the most confusing point in the world. But roughly, if there's an identity service required by the Nexus, it won't have to be. You won't have to choose a Microsoft identity service for anything. You would never understand that from that thing. I told you the Nexus source code will be made available for review. Okay, so here's my favorite. We could actually rewrite this as the Ross Anderson. What's wrong in the Ross Anderson stuff? Well, NGSCB will not censor or disable any content, period. It would be the end of the world if we did that. That doesn't mean you can't write an application that'll do that, or you can't write a Nexus that will do that. But we're not going to write a Nexus that does that. And
your slide says will censor.
Huh? I'm missing a knot? Oh.
The knot's upstairs.
Will censor? Oh, yeah, that's an important knot.
No, that's the misconception.
Oh, yeah, I'm sorry. Yes, I'm sorry. Yes, sorry. Thank you. It's a misconception. Yeah, you know, I did this. Yes, it is a misconception. Thank you. There is no policy in the Nexus except user policy. We were not going to lock it. We'll not lock out any vendors. You don't need signatures to use either the hardware or our software. This is actually an interesting one. I think it's not a super virus setters. I mean, you can encrypt viruses. You can do whatever you want. But the effect of the virus is limited to the program. And you know what? If your trusted program wants to hand the content, active content to a virus checker, has every right to do that. And I better be a virus checker on the right-hand side, incidentally, just so you don't leak the content. But NCA is not debuggable. I'd have to go through the long story here. It is debuggable. You can debug the Nexus. You can debug applications. But the identity of a debugged version of the application, not the code, but the identity, is different from the identity of the non-debuggable application. So you could literally get a program, a right-hand side program from Adobe, change its identity in a way I'll tell you in a minute. So you can debug it. Now, it'll have access to a certain set of secrets because of that program identity. If somebody is relying on those on the processing being secret, they'll say my content will only be decryptable by non-debuggable versions. But you can debug, reverse engineer NCAs just the way you reverse engineer anything.
Is there some kind of convention or service that...
Yeah, if you wait 2 slides and I'll tell you how actually that works. It has to do with the application manifest.
I take it the Nexus will not only be distributed in clear text, but would also be public domain in the sense that you will assert no copyright or...
No, that's a wrong thing to assume. It's available for review, but it doesn't mean anybody can take the Nexus and we have no copyright on it.
So if I want to come up with my own Nexus...
You can write it an independent Nexus, but you can't just take our Nexus.
Okay, but I've reviewed your Nexus.
Yeah.
And so I would have to rewrite my own in a way that makes sure that the similarities are in the idea, not the expression.
That's right.
And, okay, so that's the copyright side. Yep. As to the patent side, will you be asserting any patent rights?
There are patents. We have not announced our patent policy yet. I would like us to license our patents so anybody can write a Nexus.
But that's a very important,
yes.
very important sentence.
Absolutely.
The fact that it'll cost some money to write a Nexus isn't the problem. But that's the thing.
Yes.
Technically, people may be able to write their own Nexuses.
Yes.
But if you don't license the patents, the Nexuses may not be right?
Yes.
Okay.
Yes. Okay. All those yeses. Yes.
The crypto that you use all standard. For example, what
AES, RSA.
Yeah, AES is a block, but what modes are you using for encryption?
Mostly CBC. For the hardware enforced, is it CBC? Actually, there's no AES in the hardware. It's all RSA and hardware now.
It's all RSA, and it's for the rest
of... I'm sorry, the Nexus, you'll have a cipher suite, and probably you'll be encouraged to use the right mode, which probably CBC in the... CBC will be the... Well, we'll support a standard set of ciphers which include AES and a standard set of modes which will include CBC. You probably should use CBC.
How about counter mode?
We'll probably support counter mode. And you know what? If we didn't, it'd be pretty easy for you to add that, wouldn't it? Yeah.
So you had mentioned Ross.
Yes.
And I think he's a little shrill on some of this issue.
No.
To be fair.
Surely not.
To be fair.
Surely you jest.
Yeah.
He never is.
But
to be fair.
But to be fair. The point is not that the platform will censor or that will lock out vendors, but it will enable vendors to do
there are 2 separate points, and let me.
And I think that's a fair point.
Yes, it is a fair point, but let me get through that. So I'll disagree a little bit because Ross's original comment was that it was designed to do that. It will do it by default. In fact, originally.
I said he was a little shrill.
Okay, I wouldn't call that shrill. I'd call it something else. But that okay. Now it is. So here's the thing potentially the bad thing that could happen if you want. So I don't think in the commercial space, commercial use, there's any real issue. I think the issue has to do with big DRM. And in the big DRM case, Disney may say, you can't run our content unless you use Palladium. And our application is going to censor content while it's running. It's going to look around, steal, remove files, blah, 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 blah. I mean, it's a pretty ambitious thing for Disney to do, incidentally, because that would certainly create a howl of controversy.
They've been very ambitious.
No, I know. So that's the danger. It's a policy danger, and I agree it's a danger. On the other hand, I guess I just don't think they're going to get away from that. And in the end, users can just say, "Nice idea, Disney, but we're not going for that." I think there'd be enough pressure so they would not do that. It's certainly it's certainly theoretically possible that they could do that, but they could do that today, right? They could write an application, and would not quite as safely, but you can only run our content in our application for lots of reasons. We got private formats, we did some software dealing, blah, 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 blah. And our application is going to run an administrator, and it's going to do whatever it wants on your machine.
Okay, so most technologies that anyone provides in any field would have some multiple uses, some good and some bad ones.
Right.
For example, a microwave could be used to dry out a wet cat.
Or a computer generally.
They don't work that well. They don't work that well at that, but there is no reason to prevent microwaves because...
Sorry.
So I would discuss this.
Yes, let's revisit this at the end.
It's important. Let's talk about it later.
It's actually very different from the Fritz chip, which does censor content a priori. It says buy a chip, but the only use of that chip is to look at what you're doing and stop you from doing it. It's not that. It's kind of the anti-Fritz chip in some way, the TCPA chip. Another thing Ross said is it refuses to run unlicensed software. And God damn it, we did everything in the world to make sure any software the user wanted to run would run. So it'll run anything, including unlicensed software. Control will be exercised centrally. If there's one thing that we wanted to do is to make sure it was decentralized control. Totally, totally decentralized control. We didn't want to have anybody rely on Microsoft or any central authority for anything. TC will remove effective control of the PC from its owner, and putting the best possible light on the Ross argument, you would say by commercial pressure, they would encourage people to run applications which did remove control of the PC from its user.
Or political in some countries.
Or political in some countries, that's right. And we would say, well, you can dry out a wet cat, but actually, as it was designed, users really are the guys in ultimate control. They sit in front of the computer, and they have increased power to stop bad things from running on the machine, stuff that they don't want running on the machines, not decreased power. I'm not going to go through this. That
would be an argument for making the hardware attacks very easy. Posting them on the net, so anyone who has physical access to the machine can, with a screwdriver, do it.
Yeah, well, we're hoping. We're actually kind of careful about what we say about hardware attacks. I hope it's. What we would say internally is we at least want to stop Radio Shack attacks.
But maybe I'm not convinced by this argument. But maybe you should make them very easy on the contrary.
It's a double-edged sword, right? If you're using it to negotiate trust, maybe you don't want it to be. So, But you could certainly build hardware that you could turn a screw, and it would break. You could certainly do that, and all we'd say is it better be obvious on the face of the certificate that comes with the machine that it's that kind of security, not the. The Nexus. This sort of goes a little bit into questions asked. It's a very simple version of operating system. No file system, which is why no file system and no device drivers, which actually sort of explains why 90% of the code isn't there. But it does have processor and thread management, obviously memory management, I/O for the I/O it supports. Everything else is IPC. Throw it over the fence and say, I've encrypted it, send it out over the network, or send it to this other application. Obviously has to handle interrupts while it's working. Otherwise, the left-hand side gets the interrupts and gets access to caches, other stuff that you want to be careful don't get touched, or don't get seen, sorry. And it obviously has a very general security reference monitor because the access rules are not only access rules that you can specify on the machine in a proprietary format. They better be ways to express rules that can come in from outside the machine. So very generic access. In fact, I've always sort of been interested in the sort of distributed lamps and a body. I might have removed that slide model. I think this actually enables that. I think it's the basis of real distributed processing in some sensible way. There's a close-up of the Nexus. Marcus, I want to get you on. So, let me talk about code identity because it's going to come up anyway. The code identity of the Nexus is its cryptographic hash, period, period, period. But that's a very brittle code identity for an application. But what that would mean is every time you got version 2 of the application, you go through some rigmarole for updating. So the code identity for a program, a user, an NCA, is the hash of its manifest. And a manifest for a program roughly consists of the following things. It may have some policy information, including whether it's debuggable or not. And it might mention its hash, but more generally, it will mention a public key. And the meaning of that public key is if somebody gives you a certificate signed by the private key corresponding to that public key, it has the identity of this program. So when you get version 2 of the program, it comes with a certificate from Adobe saying this hash is the same program as version 1, and it automatically gets access to the same secrets. And that's why you can take a program from Adobe, change the debug flag, no debug flag, to debug it. Everything, software is the same. Everything works the same. It just doesn't have access to the same secrets.
Where is that private key?
And Adobe keeps it in the vault somewhere.
So, are you building infrastructure to do revocation?
We as an application company? Microsoft as an application company?
Is formerly Palladium going to have some kind of support? So you're building support to use these keys, but not to have them revoked.
The app. Are we? I guess we're not. We're not, right? We're totally neutral. The security.
I mean, a sort of more nuanced answer to that question is there is support for revocation expressible in the security policy of the machine. We're not going to go out and aggressively encourage the formation of centralized entities that will provide this revocation.
Okay, so I'm okay on what you said, except the first part said there is support in something, and I don't...
Expressing it in policy. I don't think we have support... Let's say we just start the program. We're going to start the program. I don't think we actually interpret the manifest and look for revocation information and check a revocation list, at least right now. I don't think we do.
So if a user has chosen to set a machine policy that were to go off to a revocation server to decide what applications can run, they could in principle do that with a security monitor that we're building. I'm not sure we're building the upper level stuff to enable that end-to-end, but that can be done. Similarly, if an application wanted to steal a secret to a set of cooperating applications identified through PKI and wanted to say, please use this revocation information, again, they could express that in the security policy.
So I understand that, and what I'm a little puzzled about is it seems like the public key in the manifest has a different, is a more first-class object than the notion of anything for revocation. That is, you are supported. One could, in theory, whatever you just said about revocation, I could have said the same thing for getting the public key. But you feel it's important to keep the public key in the manifest.
No, it actually isn't. This is an optional. I can, towards the end of the session, I would be happy to give you the current position of how an application is identified.
What about... I'm more worried about the idea of this attestation implying that I'm running on a Palladium hardware. If I've compromised one Palladium box, get its keys, I can obviously build a software version.
That's right.
So if I'm talking to Jeanette's box,
that's right,
and it comes back with this key, right, I have no guarantee that she's actually...
Well, you never have a guarantee. So maybe this is a follow-on from the revocation question. How do you know that there's a compromised key? And you can know that. Maybe the manufacturers will keep a sight of ones they know are... But there's no mandated... So you, on the other side, Jeanette, when you're talking to Jeanette's machine, your application may look at that and consult 50 revocation lists before they decides to go ahead.
Doesn't this sort of defeat, though, the corporate secure remote window model?
Well, no, I don't think so, because it does raise the bar. Right now, your employee not only has to accidentally set his machine wrong. He has to have mounted a several $100 hardware attack for the sole purpose of getting.
No. You had to go to the news group where the one guy in the world had.
Oh, but you can in that corporation you can consult that news group and not decide not to open up a panel to the guy with the broken key.
No, I mean, some guy hacks one Palladium box.
Right.
Publishes
the key on the internet.
An executable on the internet.
Okay.
That makes this machine now look like anybody that talks to a Palladium-enabled box.
Right.
I mean, it's true that conceptually the the home office can keep track of, hey, everybody's using the same key, coming from these different IP addresses. But
without more abstractly,
zero knowledge protocol will.
yeah. Okay.
Well, but that you could, if you broke the hardware, you could do the zero knowledge protocol.
So that's what I mean. That it won't even look like it's the same key if you.
Well, no, we'll try to do something about revocation. So, but let's sort of cut to the chase about this. It is true, if you break the hardware, somebody could rely on the attestation and be misled. Now, they could check whatever they wanted to check that would make them sort of remedy the fact that they were misled, including revocation lists, blah, 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 all that stuff. But there's unless you can perfectly guard the key, which we do not claim to do against hardware attacks, there's nothing to do about that.
Well, it suggests that we're going to need an infrastructure for.
Well, and again, so I'll talk to you guys separately about this. So Microsoft, are cautious about Microsoft mandating a revocation. I agree, there needs to be revocation.
Not just a revocation, but perhaps you could split the secret key or the secret file that you have and have some sort of a server to enable that key. So that if your machine is stolen, that machine cannot be unable to run.
Yeah, you could do that. Yeah. Let's talk later. Debugging next. I think I'm going to have Marcus come up. Oh, well, here it is. But I think I took Martine's name off it. Oh well. So this is what I think it's actually good for. I think this. So to answer Fred's question, I think ultimately, sort of the big idea, the big concern I have about computers in general is they're more and more powerful. They talk to networks more and more. Unless there's a solid mechanism to making sure that you're not attacked, that bad stuff is not happening, eventually will decrease the value of the PC. So it's not merely, will I buy the extra hardware because I've enabled 2 more applications that I really want, although I think it's important to talk about that. I think ultimately, in a world where we want people to use PCs for more and more and more important things, more and more often, talking to more and more networks, eventually if there's not a mechanism, I'm not quite sure how we get to pull this off. And eventually we can't just revoke their hardware and say, okay, we're going to start over again. That's sort of my big, well, I'd like to see it done, and now we're going to have Mark.
Before you go, a small question.
Yeah.
You talked a bit about threat modeling, and yesterday we heard a lot about threat modeling from Brian Howard and friends.
Mike Howard?
Mike Howard, sorry. Did you ever use their method?
The stride method? We do that, but we're probably more hysterical about that sort of stuff than they are. And they're pretty hysterical.
Yeah. So what did you learn by doing that?
I don't think we're finished yet. First of all, you can't really do it until after you have the really ultimately final version, because the attacks have to do with details of how you implement it, not simply the big ideas about how you've implemented.
You talked a bit about how you use it early in design and so on, but
well, you do, but you can't actually finish it.
Well, sure, okay.
Until you finish it. Okay, now Marcus.
Hi, my name is Marcus Peinado. I'm an architect on the Palladium team. So I have a couple of slides here on which relate to the so this picture which we saw with the left-hand side and the right-hand side. I will try to motivate where this comes from. I'll try to present a couple of...
Keep talking.
I'll try to present a couple of design choices and alternatives, and I will say how this can be implemented. So I'll start out with a few slides on requirements, and then I'll go into the system architecture. Just fell off. So we are certainly not the first people to try to build a high assurance system. There have been quite a lot of these systems over the years. However, we're facing a couple of requirements that differ from, or that at least go beyond what many of the systems in the past had to deal with. And actually, most of our security requirements are not that breathtaking and new, but we're sort of the the additional difficulty we're facing is related to the fact that we're trying to sell this into a mass market, and not just a mass market, but essentially the PC. So what does this mean? We are essentially dealing with an open architecture. John said that before. Any software runs, but not only that, but also any hardware runs. So any company anywhere in the world can produce peripherals and PC components. They all get stuck together by an OEM, and that just leads to a large number of and a great diversity of hardware configurations. Next thing we have to deal with is legacy. The PC has evolved over decades. At the same time, we cannot just go off and say we'll build a completely new system from scratch. We have to leave things in place, or in many places, unchanged. So no fundamental changes to the PC platform hardware. We cannot just go off and say we want a new CPU and everything combined in a new way. Also, no fundamental changes to Windows. And essentially, most peripheral hardware, USB cameras or whatever you want, should just continue to work without changes. Next thing is performance. We're going to make a couple of modifications to the hardware and to the software, but these modifications should not significantly deteriorate the performance of your computer. And finally, cost. John has talked a lot about this. Whatever we do, it cannot lead to a significant increase in the cost of PCs. Our security requirements, I think a better way to say what's on the first half of the slide is what we said half an hour ago. We want safety. We are willing to compromise on liveness. But we want high assurance for these properties. And I'm not going to say very profound things about how we're going to get high assurance, but the one thing, the one fundamental thing that I will talk about is how we try to exclude large amounts of code which exist on personal computers from our trusted computing base. And that includes the BIOS, option ROMs, device drivers, and essentially the Windows. Good. So those were the requirements. Let us look at the architecture. And I'll start out with 2 or 3 alternative designs or approaches which people have taken in the past. And the first one here is simply probably the most well-known approach, which is you start out with something like the Orange Book, and you build a high assurance system from scratch. There's a reasonable number of systems that have been built along these lines. The one thing about these systems is they were not designed for today's mass market. I mean, they were not designed for an environment where hundreds of companies build different kinds of hardware components, stick them together, and then you can sort of modify the operating system in arbitrary ways. So the second approach that people have taken was sort of to take a mass market operating system. You start out with the mass market, and you add security features to it. And an example of that would be SE Linux, where people have essentially taken a mass market operating system, Linux, and added things like mandatory access control to it. Yet, the question is, so our problem with that was, what about assurance? We still have a tremendously large trusted computing base consisting of, well, a large mass market operating system and a very diverse set of device drivers. Yet another approach is this, what I'm calling here the dual system approach, in which is sort of coming closer to what we're building, where you take a mass market system and you take a high assurance system and you somehow try to stick them together on one computer. And examples of such systems are the Perseus system in Europe. And if you want, another example would be you take your computer and you add a secure coprocessor. They have like a hardware separation between the two systems, but it's sort of the same idea, or at least a similar idea. So in software implementations, you need a base layer that isolates these two operating systems. And in practice, this base layer could be a virtual machine monitor. It could be something like an exokernel or a microkernel. And in the concrete case of the Perseus system, it was a microkernel. The base layer, the thing that sort of lives underneath these two systems, must itself be a high assurance system, because otherwise it can't isolate them with high assurance. Yes, so and the problem that we saw with many existing systems, and in particular with things like Perseus, was that the base layer still had to contain a large number of device drivers, or just a large amount of device driver code, and at a minimum, DMA device drivers. Good. So another high-level overview of what NGSCB is about. So from this point of view, we're building a dual system with a software isolation layer. In this talk, I will call this a security kernel. I'll try to relate this to notions such as virtual machine monitors and exokernels. And essentially, what does the security kernel do? In addition to, so it isolates these two guest OSs, two or more guest OSs. One of the main differences between what we're building and a traditional virtual machine monitor is that a virtual machine monitor tries to virtualize all hardware devices. That means the virtual machine monitor knows how to talk to all the hardware devices, and as a result, it contains effectively device drivers for all these hardware devices, and then it makes it look to all the guests as if they had their exclusive device. So what we're doing instead is we're going to not virtualize these devices, we're just going to give them to some of the guests, which relieves us from the problem of having to have this large code base of device drivers in our monitor. And we have one special guest, which is Windows as it is today. As I said in our requirements in the beginning, we need to maintain the mass market functionality of Windows. So the basic system idea is we run something like an isolation layer underneath Windows and the Nexus. It tries to, the difference between a regular virtual machine monitor and what we're building is that it's essentially trying to A, not have device drivers in it, and B, it's trying to give at least one guest a preferred status in the sense that it itself gets to operate fairly directly on the raw hardware. And that's sort of fairly reminiscent of what used to be called V equals R mode in the old days. Good. So here's the picture. That you can look at this as a modification or a version of this four-quadrant picture on John's slides. We have we have the hardware here with a large number of devices. We have what I've called the security kernel or machine monitor, which tries to isolate several guests. In this picture, we have two guests. In principle, fundamentally, there's no reason why there couldn't be more than two guests. In practice, with the hardware that we have today, there are certain difficulties to extending the number of guests beyond two, but we can talk about what these difficulties are later. But one thing to notice is that unlike a virtual machine monitor, the security kernel does not contain real device drivers. Most of these device drivers live up in the guests. So for the rest of the talk is essentially I'll say how the security kernel manages DMA devices. I'll say how we implement isolation between the different guests, and I'll show a little bit about some performance data from a prototype implementation that we did. So how do we handle DMA devices? As you could see on the picture, all the device drivers live in the guests. That includes device drivers for DMA devices. So effectively, we allow each guest operating system to program the DMA devices directly. But at least on existing PC hardware, there's a problem, because if a guest gets to control a DMA device directly, it can essentially program the DMA controller to access any piece of physical memory, and thereby essentially circumvent all access to memory, all access restrictions to memory. So in order to enable this mode without, so in order to block this door, we have worked together with the hardware manufacturers to introduce a fairly basic hardware-based access control mechanisms for DMA accesses. So there is at least one, but probably more older systems which did something similar, and SCOMP is the SCOMP system did something similar. So we're introducing a hardware assist. It's going to it's going to protect all of physical memory and essentially all memory mapped devices. Essentially, how does it work? For each page, we're essentially going to allow authorized software to set one bit, and that one bit says whether this page is accessible by DMA or not. So this setting is enforced by the chipset, by the memory controller. One of the things to notice here is that this one bit scheme provides limited expressive power, and it is simply the result of the trade-offs that came out of the negotiations between us and the hardware makers, which ultimately the trade-off between complexity and functionality. So that's, yes? No, it's not a page table. It's so imagine on the controller. It is one bit per page, but essentially the way it works is so on PCs, DMA devices operate directly on physical addresses, and now you can essentially set one bit per page, which will instruct the memory controller to essentially block accesses to certain pages.
What would happen? It would get
the DMA controller would essentially get either all zeros back or nothing back or error back.
Where is that bit per page stored?
It's stored in main memory.
Protected, isolated address that the DMA controller knows, and that's perceived as the address of the mask that it uses.
It is put into an address that the main memory controller and the chipset knows, and it will essentially take the bits out of there, probably cache them, and yeah.
And how big is a page? 4K bytes?
Yes. Yeah. So part of the reason why that's just one bit per page is how much. What's the question? How much memory are we willing to sacrifice for this?
And this is the limiting issue for multiple.
That is one of the main difficulties in going beyond. I'm not saying that it makes it impossible, but it's certainly, if you want to go beyond 2, you have to be somewhat more sophisticated in that.
Because of the size of the tables.
So 1 bit.
Because it's one bit.
So because it's one bit, it essentially allows you to.
Assume you change the 1 bits are in a table, and the address of the table is in the memory controller.
Yes.
Isn't it wired in though, isn't it?
So I assume that you would reload the address of the table when you wanted to switch.
Yes, that's what I meant by yes. That is possible. It leads to a couple of different. Yes, it is possible. It requires a bit of sophistication, but that's what I meant by it's still possible. But we have to.
Just because you switched OSs, you haven't switched devices. So the devices are asynchronous with whatever this table is set up.
You have to synchronize all the devices to the switch.
Okay.
Okay, so that was one of the So essentially, this hardware enforced DMA protection is one of the main concepts we have here. So next slide again. The next slide again makes all this up a little bit of the difference between what would be possible in general and the practical limitations that we're dealing with. So ideally, you would have the SK be some sort of a distributor of devices to guests. So the SK knows which devices exist. It can assign them to guests, and then essentially once the SK has assigned a device to a guest, that guest has exclusive access to that device. Ideally, the SK would essentially receive all interrupts and dispatch them to the guest OS that owns the corresponding the device that issued the interrupt. In practice, at least initially, the SK may not be able to control interrupt handling. And there are a couple of, again, hardware problems. You should probably not get into them right now, but I'll be happy to discuss them later on. So essentially what's probably going to happen, at least initially, is that we are going to have a fairly static allocation of devices to guests, and in particular, most devices are going to be owned by Windows. Good. So that's what I have to say about DMA management and device management in general. Next question is isolation. We have something like a machine monitor. We have several guests, so we have to isolate the machine monitor from the guests, and we have to isolate the guests from each other. And essentially what this means is the goal is to sort of enable guest operating systems to have exclusive access to resources. So the question is, why not just build a virtual machine monitor, or why not just build a regular virtual machine monitor? So first of all, there's this device driver problem. We're just trying to remove device drivers from our monitor. But so that's one difference. And sort of associated with this difference is also a certain limitation of existing virtual machine monitors, at least for PCs. I mean, most of the time, things like Connectix and VMware work just great, but there are certain things which they don't do that well, or which they do only very slowly, and these are mostly related to device access. If you want to use the latest and greatest features of your graphics card, you typically can't do this with VMware or Connectix precisely because they would need to include all the device drivers for your latest video card in there.
But the difficulty I have with what you're saying is, and this may just be a packaging issue. The VM370 used to have support for devices to be owned completely by a guest operating system. And this was not done by mapping it and remapping it. It was done by something like virtual equals real. So using a VMM doesn't automatically require you to support all the devices. You could build a VMM which passes all the devices up to machines, and it's still a VMM, and you don't pay any of these difficulties.
So I try to actually understand how the old IBM machines were managing virtual equals real, and the impression I got was, and maybe that's the wrong impression, and then I'll stand corrected, that there was the things that were operating under virtual equals real could essentially subvert the hardware, could subvert the VMM. So guests in virtual equals real mode, the VMM was not protected from guests in virtual equals real mode. I may be wrong with this, but that was the impression I got. But I mean, probably more generally, if you say that in the old IBM days, you would allow virtual equals real guests to essentially manage their devices directly, then I guess it may just be the difference in what we're talking about may just be in the name. So one of the points I'm simply trying to make is that we cannot leave the device drivers down in the isolation layer, and we can call this a virtual machine monitor or something else. The other thing that's sort of this. The second bullet point here in the middle is not just at least if we look at existing virtual machine monitors and sort of existing virtual machine monitors on the PC, which are sort of constrained by what PC hardware looks like as opposed to what IBM hardware looked like, there are certain things which they just don't do that well. And essentially when it comes to Okay, so what am I trying to say? I'm trying to say that today the virtual machine monitors which exist for PCs today don't export devices, and as a result of that, there are certain limitations to device management that they can do. And examples are sort of, you typically don't have the latest and greatest video card driver in VMware.
Mention VMM, you have sharing in mind, essentially, right?
Yes.
Because if we don't share, if we just run one guest OS, that's what SK is. And if we share physical devices, then we pretty much have to virtualize.
You don't want to share a physical device. We understand that sharing physical devices is a security racket.
Well, let's say a video card.
You can partition them.
Well, what about video card? You have one video card.
But you already bought the problem of sharing the video card. You did that in version 1 when you didn't have a VMM. So
well, actually it's not sharing, right? In the version 1, it's a special surface that's used by the SA. Yeah, it's a physical share, partition. But if you want to run two guest OSs in the general case, then you have two copies of the video device drivers that you have to synchronize, make them coordinate. And then you have to put some logic into the virtual machine monitor. Or you adapt the video card device drivers so they know how to coordinate. It's not a simple problem of mapping the physical device space into the guest OS. I mean, it's not that simple, right?
I understand what you're saying, but I think you're making the problem, you're not being fair in the comparison. If there's the short term, the medium term, and the long term. In the long term, if you had a VMM that supported multiple virtual machines, you might have a virtual machine that managed the screen. And that the cost of that is putting in communication between virtual machines. But once you do that, then you have a way to manage all the devices because...
Correct.
Okay, so the long term actually has a very elegant solution this way. And the design that you have doesn't have a long-term elegant solution. The short term, which is what you're doing now, has you making changes to various pieces of Windows. Right? You have this list of things that you have to change in Windows.
Which is very small. It's
very small.
200 lines of code right now.
Yes.
You're starting to couple these two things.
Yeah.
And I start getting nervous when you start coupling them because all of a sudden I'm not convinced that the trusted computing base is as isolated as it was. I know you're going to try hard for that, but I'm trying to come up with a design that you don't have to try all for.
Yeah, no, I understand.
So if you do it in the short term, then you don't have to do those changes. You could build the same level of brain damaged functionality by not multiplexing devices and just passing them up through. And so it's a cleaner design at the short run and has about the same functionality. It's a more elegant design in the long run. And I don't know, the setting up about the middle run, I'm not convinced that one is a win or the other is a win because you have to factor in the growth of applications and some of the potential of having multiple virtual machines as an advantage that would foster growth towards the long run that you can't support in your middle run. So I don't think your analysis is fair.
Okay. Let's. It's 11:15. I do want to suggest we get through like the next 5 slides up to where we get to the event counts, and then Fred, probably if you want to stop and just have a discussion, then that would be fine, or keep going. But actually, I do think we should do the isolation stuff.
Okay. Anyway, so one last word on the slide. So the point of the slide was simply was not to say that we couldn't have a security kernel or monitor at the bottom with many guests on top. So this slide is simply supposed to say, why not just take VMware out of the box and run on top of that? Good. So next, a slide on which has some more hardware details in it and how things are going to, how we're planning to use them. So today So what we have here is a native operation of an operating system on something like an x86 CPU. We have an operating system kernel running in ring 0 and applications running in ring 3. The traditional, and by this I mean stuff like Connectix or VMware. But, I shouldn't use any names here, but essentially you put a virtual machine monitor in ring 0 and then typically do some ring compression or push the operating system kernel upwards. Instead of that, so pushing the operating system, in our case Windows, upwards would at the very least have led to some very difficult negotiations within Microsoft. So we are very happy to use a new hardware feature which actually allows us to leave Windows exactly where it is today and not make any modifications to it. Leave Windows in ring 0, whether we're there or not. New hardware is going to have something like a ring -1 in which we can place our machine monitor. And other guests can live in ring 0 isolated by the machine monitor. Okay. Good. How do we actually implement the isolation? Well, I would describe it as a version of what every machine monitor, what every virtual machine monitor in the world does. The classical algorithm for this is called shadow page tables. We're using the V equals R optimization for the Windows guest, for the main Windows guest. And we're using a couple of further optimizations based on a specific behavior of, since we're not trying to build a generic virtual machine monitor, which, well, we could do that, but for now we're not doing it, which could sort of host an arbitrary operating system. We are taking the freedom to sort of optimize this thing for specific things that we know that Windows doesn't do. The security kernel grants guest OSs exclusive access to a resource such as a page of physical memory by allowing it to map it. And every instruction of the guest operation that could change the virtual to physical mapping gets trapped by our SK and evaluated and filtered. And examples are sort of write to CR3. CR3 is the page table, is the register in the x86 CPU that determines where the page tables start. So there's a slide here on the next page which tries to, so this should just be something like the page table picture out of a standard operating systems textbook. We have different pages. At the end here, they're owned by different guests. In addition, we have these page tables, which themselves are pages. Assume we have guest 1 running, and these are the page tables for guest 1. We allow guest 1 to establish mappings into the pages which we've assigned to it, but not into the pages which we've assigned to other guests, indicated by the red and green colors. In addition, there are limitations to the mappings that this guest can establish into page tables. So we do not want a guest to just map pages of other guests, and we do not want a guest to be able to directly edit page tables. So that's just a somewhat optimized version of the standard shadow page tables algorithm. We're doing so now. Actually, can I go? So now, if you look at this algorithm, you'll see that in order to establish these, so the algorithm has to maintain a couple of invariants, such as no entry in a page table should actually point into certain pages, which may require you to search the entire page table whenever you the entire set of page tables whenever you edit something. There is a host of optimizations and essentially time-space trade-offs where we've been experimenting with a couple of them. Let me just go through into one of them, given that we have sort of round-robin scheduling, which means that typically something that was a page directory, that was a valid page table the last time previously is likely to be a valid page table in the future. We sort of cache these pages, and so we maintain a couple of caches, and it's probably not worth getting into these things since I'm being encouraged to finish soon.
Try to get the timing numbers.
Okay. Good. So we built a prototype implementation of all of this. It implements isolation, the isolation and hosting components of the security kernel. The initial test bed was just an unmodified PC in which we instrumented the operating system to simulate some of the hardware changes. In the meantime, we've got this running on the real hardware as well. Changes were mostly simulating this ring -1 by making certain instructions trap. And goals were simply to check for surprises, see whether whether there are any surprising behaviors in Windows that we did not expect. Check that our validation methodology for sort of assuring the bug freeness of this code was feasible, and finally just see what kind of performance can we get, where can we tweak things. So the final implementation of this is about 2,000 lines of C code. The actual isolation algorithm is about 1,000 lines. We formally specified this thing in first order logic and actually verified its correctness with a theorem prover. And the C code that implements it is directly derived from the formal specification. I'll have a couple of timing measurements. They were made with a prototype which was not particularly optimized. And the testbed is just a regular fast PC with 1 GB of RAM. So the first set of measurements we had was we took one of these macro benchmarks, which people typically use to test their hardware. We used Winstone 2002. So what do we see here? We see we've listed the different types of changes of instructions that can change the page mapping. And essentially CR3 load is, so this one happens when a new process gets created. Apparently this benchmark created 63 processes. CR3 load, after we've already seen it before from the cache, which happens due to round-robin scheduling, happened about 1 million times, but was a couple of orders of magnitude faster due to our caching. And then you have the different levels of page table and page directory edits, which once again occurred in large numbers. And these kinds of numbers are mostly there to guide our optimizations.
In the first one, in the new case, the 2 milliseconds are for each of the creations or for all 60?
This one here?
No, the one right above, yeah. The new.
This one?
Yeah.
This one is when you create a new process.
For each one of the 63,
yes.
pay 2 milliseconds.
Yes.
Okay.
And so this is what you pay on process creation. This is what you pay on when you get scheduled. Okay. So next slide contains a couple of micro benchmarks which we wrote. I guess I won't get into what exactly each of them does. They sort of fall into two categories. One is sort of device access, and the other one is page table memory kind of access. And in the last column, we did the same experiment. We ran the same benchmarks on VMware, mostly to. I mean, it's a bit of a strain. So, I mean, this is not here to beat up on VMware, but mostly to justify why the option of just take something and run it on top of VMware had some problems associated with it. So we had disk I/O. We just try to read and write large amounts of data to disk, and the number in this row, the numbers in this row correspond to the throughput in megabytes per second. And with our architecture here, we have a slight deterioration in the throughput, but it is slight as opposed to VMware, where it is quite noticeable. Direct draw is one of these things which use the video card features quite heavily. Again, we have only negligible performance degradation, whereas under VMware it doesn't even work. So the next line has a similar graphics benchmark. So the last three rows go into page table edits and context switching. And again, there is, in two cases where we're significantly better than VMware. In one case, we are slightly slower than VMware, and essentially seems to be mostly a function of the particular time-space trade-offs that we used versus the ones that VMware used. Sorry, I'm rushing through this. Finally, once again, the Winstone benchmark, which at the end outputs a score. So different columns here are supposed to indicate, I guess, higher is better, and sort of comparing native VM. Our design as it is. Our design with extra delay cycles to account for possible overheads in the new hardware, and VMware. And again, we're sort of somewhere in the middle between native operation and a virtual machine monitor. Good. So just to summarize what I've talked about so far. So we're building a dual system, or possibly a more than dual system, but essentially at the minimum we have a mass market guest and a high assurance guest. Much of what I've talked about has been how to make something like a virtual machine monitor small, and the main point was to get rid of device drivers in there. And we have introduced, or we require, a couple of changes to the chipset and the CPU, and probably the most fundamental one of these is the access restriction that allows us to move DMA device drivers up into the guests. So, where did John go?
We need to have a discussion, so.
Okay. Well, I was just wondering whether I should just continue talking or whether we should have the discussion now.
John is right outside.
Okay. Can somebody?
So the floor is open, folks.
Could you explain again why the memory allocation was so much more expensive?
Memory. You mean on the performance slides there?
Yeah. Go back 4 slides.
Okay. This one?
Yeah, so that row was
Okay. Which row?
the second to the bottom.
This one.
If I can comment on this. So actually, that test actually really stresses the validation algorithm because it allocates a 4 megabyte chunks in virtual memory space and then commits each first page in chunks. So it involves page directory edits and page table edits. So you have to check both page tables every time.
And essentially native Windows just goes ahead and adds a page table, whereas we have to trap there and check whether our invariants still hold. And I guess VMware is not much different. So that's sort of we make certain operations slower, and that thing there just emphasizes only does operations which get much slower.
So you have real hardware now, you said. Have you rerun these?
Yes, we have real hardware. This stuff runs there. We have not gotten to updating these numbers, but from what I can tell so far, there's no big difference.
Okay, so you think this?
I believe that these numbers are self-representative.
But it wouldn't be fair running the real hardware right now because the optimizations haven't been done.
Are there bigger picture questions?
Paul, why don't you talk too, since we're at the discussion phase of the...
I'd like to get back to the top 3 or top 5 applications.
Go for it.
The topic of applications?
Yeah, I think anything. Yeah. So you had this pretty long list, and so let's drill down onto the few that you think are most promising. No.
Let me talk about. So I talked to Fred about this a little bit. So in some sense, my fuzzy thinking about this is that you need to do this to preserve the DC ecosystem eventually. It'll eventually collapse on itself. It wouldn't be enough security, and you can't just say the day it collapses, okay, we'll fix it now. It's collapsed. So sort of as a meta comment, me personally, John, if it were my money laying on it, I think it's a reasonable bet to make, even if you don't have a killer application quickly. Plus, we get into all the trade-offs about.
That's kind of insurance. Is that your insurance? Is that your?
Yeah. Okay. So I think the current thinking is the 5. And actually, you might have to tell me. I don't know what the 5 top applications: remote desktop, cryptographic services on the right-hand side, IAM, mail.
Document signing.
The
other things that we're looking at are things like right-hand side domain logon, protecting the syskey.
There's also be a rights management client, which means an application can ask it to evaluate rules on the right-hand side. And actually run on the right-hand side, so it will enable both small and large rights management. But as I said, I don't think we believe there will be audio and video applications from Microsoft that will SIM ship first person. Although I expect those to happen soon. Actually, my main worry is if we to tell you the truth, is that somebody will beat us there once we ship the application, ship the platform, which. That's like
is DRM the killer app?
I don't think there's the killer app. Although if I'd say the killer app, I think it's basically PC help and sort of distributed services across. Whether you get on a network, what you trust happening across that network. So I me, John, and I could be the wrong guy because I always get yelled at by some vice president about that. I don't think there's the killer app. Just like it's a little bit more confusing in operating systems. But.
Do you have groups that are beginning to write apps?
Well, we write most of the applications, and we have groups that are certainly considering using it. But we have to be careful. We have to divide our time between actually writing stuff which works and helping other people write stuff that works. And it's not an enormous group right now, despite what it sounds like. There are 48 people right now, and I think we'll have about 90 by the time we're done.
What's the split between dev and test? I'm sorry. That's right.
Test is the ratio. The ratio we're shooting for is 1 dev to about 0.75 PM to about 1 to 1.25 test, but it's a little bit different. Our test is all SDev, not standard test, no doubt.
So I want to come back to the applications. The ones you enumerated are all sensible, standalone, increasing assurance kind of applications. But how does it fit into Windows? Yeah. People, Microsoft wants the computing experience to be more secure, and there's this effort to make Windows more secure, a variety of nice efforts. But it sounds like you don't see Windows ever migrating from left to right.
Not all of it, otherwise it's the same deal all over again.
Well, look, there was a time when NEC was about to announce the alpha, and VMS was completely unmanageable, and the solution was thought to be, let's have a new operating system, and we won't have to worry about VMS anymore. That'll be legacy. And that's how they thought now, they never did that for a variety of reasons, but you're sitting at the same precipice, if you will. But you're not talking about moving Windows functionality across.
Well, yes and no. Let me say certain three things that I mentioned.
Yeah, I'm worried about Word and PowerPoint and all those big things that are...
Well, here's that thing. I'm not saying this is a perfect, crisp, well-defined answer. I'd say sort of three things. First is, we do expect some components of big applications. Second, we have this notion that we haven't described, and probably is a longer story in itself, with how the right-hand side can sort of extend some kinds of protection to the left-hand side without much modification of the left-hand side. That will be in V1.
That's through the rights.
No. With the rights management, that's a separate application. This is more like, watching things, protecting things, that executable pages that are trying to be read or modified, that sort of thing. There's a bunch of stuff we think we can do to help the left-hand side. It is a major problem because everybody else looks at us in Windows and says, you're just building another operating system under us. And we get criticism from both sides. There's not enough in the left-hand operating system, and eventually you're going to kill us because it's all going to go to the left-hand operating system. So I would say in the current design, and again, not the big future thing about to what extent you actually have VMMs. There's one other thing we have an MLS project that will actually also try to benefit from this. But my own view right now is in the next couple of releases, it's not everything will move over and nothing will move over. It's some important stuff will move over, but it's not all of Word, and it's not all of Excel.
And who decides what moves over?
Well, for those things, it will be Office.
So there will be someone in Office who will say, for this new platform, these components will be on the right-hand side.
Yeah, right. And again, when I say move, that means there's going to be two versions.
Exactly.
Sorry, not two versions. There'll be one version. If you have the hardware, you'll be able to get that functionality. If you don't, it'll still work.
Right.
But
and then for all the things on the right-hand side, isn't there a formal verification that you want to will actually have to do to...
Well, it's a funny thing here, especially for something that's been a big application. There would certainly be a verification. One thing we didn't talk about was moving managed code to the right-hand side, which we would like to do, which will help things a lot.
Managed code in all the libraries?
No, don't say all the libraries. Again, we go for a minimalist version. So the entire managed code environment, we would definitely, it's almost the same answer as Word. We would never move all of .NET over to the right-hand side. But we would move a CLR and some limited interface. The CLR touches about everything, and with 32.
Back to my earlier question, anything on the right-hand side that Microsoft moves over, anything that Microsoft moves over,
right,
that's Microsoft stuff, to the right-hand side,
right,
isn't there some kind of guarantee you want to provide your customer?
I wouldn't say the G word, the guarantee word. I would say they're subject to a high scrutiny verification process. I'm nervous about saying guarantee or total verification because I've never seen it work.
Just tell me what the verification process would be. Would it be above and beyond the kind of testing that you do?
Some of the applications will actually be built from specifications. I mean, some of the things, MLS, for example, will probably be built with the model in mind. So as you develop the code, sort of standard Orange books, as you develop the code, you have this sort of process.
But what about existing apps? Like
existing apps can't move. I mean, you have to write code to move to the right hand side.
You said some of the components will move.
Okay, that's it. Wrong word. I shouldn't use the word move. There will be a new version of the components that runs on the right-hand side that is some shim will make it API compatible with the thing that's there.
So
yes.
Going back to the applications list, my take was that the ones that didn't have very much to do with user experience seem very plausible, but the ones like secure email, where the user was involved, seem very iffy to me. And maybe I'm way off, but just users will be very inconvenienced by having these two email systems, and one of them is kind of brain dead, but has this nice.
So ultimately, we have to user test and see whether all that appeals to people. That's certainly true. I don't know the answer a priori. There may be things which mandate some of that, health records, that sort of stuff, that mandate that kind of secure collaboration. And there may be particular domains in which that's used. But I don't. The bigger question about whether mom and pop will use secure mail on the right-hand side is certainly not an answered one. We had that one. She just patiently had for a while.
To render an HTML subset, you can get it online. There were things like transaction authorization, secure email, signing documents. So, evaluation of what applications to go to from the perspective of looking for is essentially transparent way by being stored some virtual printing drive where you have to get documents relatively small changes. Like an example of this is how we strike existing applications. Absolutely, but I'm certainly little secure, which it seems to be where this sweet spot is really frustrating.
So I'd like to spend just a couple minutes and make a statement to kind of add to some awareness here and get other people's reactions. Some people may view this as a partial rant, or others maybe not, because this is taken outside of the computer science aspect, and it's more from my viewpoint as a philosopher as well. And I've raised this for the folks at Intel because I'm on the TCAAB advisory group, and I haven't had a good response from them either. You said it's based on the thought technology is not value neutral. And for you to say that people are free or not to use this and the software that's in place. And that may be the case, but there's an awful lot now that has achieved a kind of de facto dominance that I think is unhealthy. Examples, there are some DoD sites like the Navy that if you want to submit a proposal, it's got to be in Word. I don't use Word. The academic summit that occurred earlier this week, I tried to sign up for it. I used 6 different standards compliant browsers, and the only one that would work was Internet Explorer. So much for standards. So when you're saying, okay, we're going to have this capability and DRM and other things, people don't necessarily stand for it. That's a very U.S.-centric view. If I'm a citizen in the People's Republic of China or Myanmar or some other country, and the only way I can connect with government services to get my pay, to register where I am, is to use this technology with an application that they've prepared for me, that monitors what's on my machine, that installs something to look for my keys, that is a very dangerous bit of it doesn't matter whether it's Microsoft or Linux or whoever else has written it, putting that capability where government or a large corporation can effectively mandate it because you're free to use it or not, but then again, you don't have access to any of the services, is a threat. Independent of whether or not the software hardware works the way you think it does, there is a threat behind the introduction of the technology. And I have yet to hear from anyone involved really any kind of admission of that threat, or how, as a corporation, you're selling to all these countries, to all these other companies. You don't necessarily want to be in a position of saying, that's evil, we're not going to sell it to you because that's going to oppress human rights. But if you're going to produce this and the entire government of China says, geez, we're not going to adopt this, we're only going to get Intel chips or AMD chips, or we're going to switch to PowerPC chips, and we're going to run Linux because you don't support the kind of things that we want to do to our citizens.
Right. So let me try to answer your question. Any technology is a threat. So if somebody said there's no possible threat from this, what do you want me to say? The PC itself, I mean, you can design nuclear weapons on PCs and simulate stuff you could never do before, right? And not in the business of, I can't stop people from doing that. Where Microsoft is not a sovereign country, so I can't stop the government of China, for example, from doing something or potentially doing something that that they don't want. So I guess, and it's kind of a squishy answer. We'd say on balance, I'd say, let me actually take Microsoft out of this. So I think on balance, it's more likely to produce good than bad. It's a very squishy statement. It's more likely.
That may be the case. I'm just wondering what you're using to model that or justify that. It's like the argument over encryption, making strong encryption available.
No, it's exactly like that argument. That's right. Absolutely exactly like that argument. And I came down the side of strong encryption in that argument.
As did I.
Yeah. And what I would say is, it's similar. So we'll do a dangerous thing, which is sort of speculate out loud. And I haven't thought about it deeply enough to say, here's the paper, or here's the clear thought. But I think
anyone within Microsoft.
No, I don't think anybody can anywhere, period. And I think it's a more generic problem. It's like, what I would say generically is, I think PCs on average did a better job of empowering people than centralized computers. They did. They made more things possible. They made actually some things more dangerous, right? The fact that people have PCs, and I don't mean Microsoft PCs, your PowerBook is just a fine example for this. I don't know how you quantify that at all, but I throw away all my PCs because some bad thing could happen. And some bad thing could happen because I have PCs. I'd say, no, forget it. I don't want to do that. On balance, it's much better.
So what I'd like to suggest from this as something, and maybe even as an action item, I don't know, is it might not be a bad idea for many of the things that you're doing with the technology that are revolutionizing the world. If you're thinking about some of the great uses, it might not be a bad idea to have some people who are thinking about the social, ethical dimensions of what this technology is going to do and give it some forethought, because otherwise you have people who see some of the dangers maybe through a lens darkly, like Ross Anderson. And there are a lot of other people who are concerned. I'm not on balance of the opinion that this is the end of the world. But the fact that it isn't being thought of by the people developing the technology,
so,
what are some of the...
It's fair to say that we haven't thought of it.
But it's not part of the overall process.
Well, yes and no. So I don't think you would look to me, if you'd look to Marcus or Paul, and say they were the best people in the world to make societal decisions in a vacuum. I would say we've tried hard with the technology. In fact, part of the reason we've had PR problems is we went out very early to groups that might be concerned about this, like EFF. Who else we went to? We went to a bunch of groups. But the outcome of all that is one of two answers. You did something stupid. If you did it a different way, you would reduce the risk a lot, or you make things a lot better. And that we're desperately trying to seek that sort of feedback. The second kind of feedback we could get is, on balance, the whole thing is a dopey idea, and it's much worse than it is good. And I think we believe strongly that that's not true. But probably also, and you know what, that discussion should happen. But in the back of our heads, we'd say the same thing probably you're thinking about what I just said to you. Boy, the way you came to that conclusion was pretty nebulous and unscientific, and I'm not quite sure I believe that. And it's not that any statement you said doesn't follow logically from the other statement, but there's something either in the beginning statements or the whole thing you don't quite appreciate.
No, there's a rigor that's not lacking. I mean, it's really easy to wonder what the problem is. Is that you wouldn't, MSR wouldn't say, well, we went and talked to a bunch of groups and we got their opinions and then we decided to do this.
Right.
It's that it's a product of some systematic research. And I think that it means part of what I would suggest, I would second what I said here, is that if you understand, and I think Microsoft does, I listen to Bill Gates talk about, we're going to have the next 15 years are going to be this, technology is going to be touching people in ways that is increasingly important for society and for all different aspects of society. And if you believe that, you have to invest in the kind of research that doesn't say, well, we went and talked to some groups or we did some focus groups. It says we actually engage in the same kind of systematic research because we take these issues as importantly, as seriously as we take technical security.
Well, the same kind of research as what?
As you would invest in technical security research. I mean, I'm not saying that the dollar amount has to be
No, I know.
But it has to be.
I get it. So I actually like the concrete because I think you have done that. You'd be surprised how unsystematic sometimes our technical research is.
Well,
and it often consists of, I'll go to the 5 people I think know this thing and I'll ask them a question, but I don't have a formal proof of what they know.
Well, I actually don't know what MSR does, to kind of
we
see
should take the hook off MSR. This is
no, or
my group's fault.
Whatever. Well, no, but I think that, the research piece of it is what would help feed into.
Right.
We had a conversation, okay, so we understand secure code, and Ira pointed out we don't have, privacy by design in the text, right? And we don't, and I think there's a need to invest in that kind of stuff.
And so, let me just sort of clarify. Are you suggesting we do it or that we contract with people to study the problem?
Maybe just to interject. So yesterday we saw a lot on the security side about threat modeling.
Right.
And there was I think, fairly sophisticated methodology which people discussed about threat modeling on the security side. And so let's say the scenario technology goes to repressive countries. And so could we privacy threat model, for example, for that socio-political reality, and then do a design of what happens, what bad things then happen if the Chinese government or some other government decides everybody in their country.
Do that
well, and also, are they any worse?
Point extra does a design.
Yeah, sometimes it's worse, sometimes it will be worse.
Right, but in a lot of cases you might actually come out and say, Ira and I were having a discussion, well, is it really worse that the stuff is happening over in the secure base? And it's like, well, no, because the same shit can happen over here, Yeah.
So you've thought of the good applications. I'm sorry to interrupt. You've thought of some of these good applications, and you have them listed as small and big protections.
Right.
And that's great. But it would be interesting to see how those are balanced out and developed along with some of the other potential questionable ones, and say, are there elements of the design that could actually be included to make some things more difficult? For instance, that might actually not change the overall security goals, but might actually enhance the protection of the individual consumer.
So, at sort of the very top of what we try to do, you might part of this may be an underlying
time out.
Real quick, we've got to take a break here. I just want to do 2 things. We've got to take some natural breaks in the back when they're taping this so they can do some things, but also we have lunch here, so we can continue on the discussion, but why don't we take 5 minutes right now to load up on chow and then carry this forward. All right?
Hold that thought, you guys.
Remember, there's no such thing as a free